At the end of Unit 5, I mentioned that we are going to be looking at solving systems of equations using a different technique than what we saw back in Unit 5. Unit 5, we saw graphing, we saw a substitution method, and we saw the addition or elimination method. Here we're going to be using matrices. Matrices are pretty powerful in that they are used to store data, basically. If you have ever used Excel, I kind of think of that like a big matrix, right? Each one of those cells holds a piece of information. That's kind of what we're getting into here, and we're going to see some uses of this in this unit. First, we're going to start with matrix solutions to linear systems. The objectives you can see up at the top there. Write a system of equations as an augmented matrix, perform matrix row operations, then use Gauss-Jordan elimination to solve a system of equations. This topic, this idea, this section is going to take a couple of videos. This is big, the work that we need to do here. So I am going to just tell you right now, we'll be looking for a couple videos to get through this matrix solutions to linear systems. You can read that big picture idea up there at the top, but basically what it boils down to is what we looked at in Unit 5 was all two variables. The physical world that we live in often has more than two variables that are happening at the same time, right? Time is changing, temperature is changing, pressure in a physics application. Things are changing. Lots of things are varying at the same time in any given scenario. So we really need to be able to solve systems of equations with multiple variables. That is what we are really, that's the true application of using matrices to solve systems of equations, is when those variables get extensive, addition and the substitution methods are just not really very good options. First, we need to define what a matrix is. It's a rectangular array of numbers. You can see a couple of examples below this in case that is not really clear. A matrix is said to be m by n if it has m rows and n columns. So we need to count how many rows and then how many columns. In this case, we have one row here and one row here. So it's 2 rows by 1, 2, 3 columns. I know this is strange, but when I learned this, the way I remembered it is I always thought rows by columns. I always thought of RC, and I just thought of that old soda, RC Cola, or Royal Crown Cola, I think it was. That's how I remembered it. You need to know rows by columns. This one's a little different. There's only one row and one column, so it is 1 by 1. That's going to be important when we get into some of our operations that we're going to do with matrices. The big question when we're looking at solving a system of equations is we continue to write the x and the y and maybe a z or whatever, however many variables we have, we continue to write those over and over again. But realistically, as long as we're keeping track of those variables and where they are, we don't really have to write the variables over and over again. We do need the coefficients, the numbers matter, but the variables don't if we keep track of, hey, these are all the x's, these are all the y's, and so on. That's what an augmented matrix does. Let me show you an example. We are going to write a matrix. It is going to have 3 rows because we have 3 equations here. It's going to have a column for the x's, a column for the y's, a column for the z's, and then a vertical bar that sort of represents the equal sign, and then the constant over on the right side of that vertical bar. So the first row is 3, -2, 1, and then a 4 over here. That represents 3x minus 2y plus 1z equals 4, that first equation. We do that for the second equation, 2x plus 3y plus 0z equals -1, 1, -12, 10, and 6 for that third equation. This next system of equations is sort of an interesting system of equations. It is a system of equations. It's 3 equations, but it's already solved for us, right? We still need a column for x, y, and z because we have 3 variables here. X equals 6 would be 1, 0, 0, 6, right? The coefficient on x is 1, no y, no z, equals 6. Then the second equation here, 0, 1, 0, 2, 0, 0, 1, -2. Wouldn't it be nice if we could convert from an augmented matrix in the first example here, something that looks like that we clearly we can't just look at that and see what our solution to our system is. If we could convert that to something that looks like what we have in part B here, we can read off our solution right away, right? I mean, this is the solution. If we can get our augmented matrix to have 1s down the diagonal and 0s elsewhere, with constants over on the right side here, we have our solution to our system. That's going to be our goal, to convert from this to this. This in part B is not the solution to the the system of equations in part A, but if we want to go from this look, this really crazy look, to something nice and clean where we can read our solutions off. The way we do that is through what are called elementary row operations. We can only do row operations. Well, let me show you what they are, and then we'll talk about why. First thing we can do is we can switch any 2 rows. Why might we be able to do that? Remember, each row of the augmented matrix represents an equation, right? This row represents this equation. So if I just flip 2 rows, if I switch these 2, then all I'm really doing is switching these 2 equations. That doesn't change the system of equations, and it certainly doesn't change the solution. This is equivalent to switching 2 equations. You cannot do it to columns because then you're flipping the variables, and I suppose you could, but you have to keep track of the fact that now we have x, z, y, for example, if you switched those, and I would not do that. You're going to confuse yourself. The second row operation that we can do is to multiply any row by a non-zero constant. And technically you could multiply it by 0, but you don't want to, because then that eliminates the equation. You just get 0 equals 0. Remember, this is equivalent to multiplying both sides of an equation by a constant, because that row represents a constant, an equation. This you definitely cannot do to a column. You can't just change all of the y's, the coefficients on the y's in the various equations, right? That is definitely a no. The last thing you can do is you can add a multiple of one row to another row, or to a multiple of another row if you need to, but we don't typically do that. I'll show you why. This is what we do in the addition method, in essence, right? We multiply one equation by a constant, or maybe two, and then add them together. So we add a multiple of one row to another row, add a multiple of one equation to another equation. That's what we do in the addition method. We're going to use this matrix to do some row operations. The notation here varies a little bit how it's done from online homework system to online homework system. I am using Alex. Some of your instructors may be using My Math Lab. Alex uses this notation, so that's what I stuck with because that's what my students are using. What this means is we multiply row 1 by 1/3 and we put it in row 1. We leave row 2 and row 3 alone. When that happens, I usually, just so I don't mess it up, I usually just copy those rows right over so that I'm not tempted to change them in any way. The only thing I'm changing is row 1 because that's where I'm putting the new equation. Well, I want to do 1/3 of that. That's going to be 1, -4, 2, 3. That is a valid row operation because it's just like multiplying that top equation by 1/3 or dividing both sides of the equation by 1/3, or by 3, excuse me. So that is okay. Now I want to do row 1 minus row 2 and put it in row 2. I am going to copy the other two equations and as they are because I'm not changing row 1 or row 3. I'm copying row 1 and row 3 because I am not changing them. I am only changing row 2. This row operation is really the third one here. Add a multiple of one row to another row. This one up here is actually 2. I think I may have said the first one, but here it's the number 2. Multiply any row by a non-zero constant. We're multiplying that row by a constant. Row 1 minus row 2 is the same thing as multiplying row 2 by -1 and adding row 1 to it, right? This would be the same thing as negative row 2 plus row 1 to meet that language up there. Add a multiple of one row to another row. But it's easier to look at it as row 1 minus row 2. So let's do that. I'm going to do that. This isn't, yeah, no, let's do this. Row 1 minus row 2 with the one we were given. So actually I need to erase this. You know what? Let's just make a note here. Using answer to part A. And I'm going to talk about why in a second here. So that's why I just copied from above. We're kind of like progressing through some steps here. Row 1 minus row 2. 1 minus 1 would give me 0. -4 minus -4 would be -4 plus 4 is 0. 2 minus 4 would be -2. 3 minus 0 would be 3. Okay, now let's use our answer to part B to do this operation. I'm going to copy row 1 and row 2 because I am not changing those. Be careful to follow the directions if you're using an online homework system. If you have multiple parts like this, it may want you to refer back to the original. I'm just trying to sort of prove a point here. We are going to multiply row 2 by -2. So in this spot right here, we're going to do -2 times 0 plus 2. that is going to be 2. The second one, that's this guy. For this spot, I'm going to do -2 times 0 plus 0 is going to give me 0. And then for this spot, I'm going to do -2 times -2. That's the row 2 entry, plus 7. That's 11. And then for this spot, I'm going to do -2 times 3. This 3 here, plus 4, which is -6 plus 4, or -2. Okay? So that's kind of what we're working on here. What I wanted to show you was, remember our goal is we want 1s down the diagonal and 0s everywhere else. Notice the 1/3 got us a 1 here. I want a 1 there. I want a 1 here, and I want a 1 here, and 0s everywhere else. This operation got a 0 in that spot. We could have done an operation to get a 0 in this spot as well. If we had done -2 times row 1 plus row 3, that actually would have worked. We'll keep working on it. I'll show you what I mean. These problems get very long. I have some steps here that you can read through. We're going to just work through an example. I'm going to do one example, then we'll probably take a little break and come back and do some more examples, because like I said, this can get very cumbersome, some of these calculations. The first step to Gauss-Jordan elimination is to write the augmented matrix. That'll be 3, -2, 2, -1, 2, -6. We are starting here with just a 2-variable system of equations, so we can see how this works on a small scale. I probably wouldn't recommend using this method when you only have 2 variables. Particularly on this one, the addition method is super easy because the y's have opposite coefficients. So when you add them, the y's eliminate and you just have x equal to a constant. You know, you'd have 2x equal to -4. But I want to show you Gauss-Jordan elimination on kind of a small scale so we don't feel so bogged down in it. What I would do here, because I don't like working with fractions if I don't have to, I would switch row 1 and row 2 and put that in row 1. So -1, 2, -6, 3, -2, 2. I am trying to get a 1 in the top left spot. The way we get a 1 is we multiply the equation by the reciprocal of what's there. We would multiply by 1/3 to get a 1 in this spot. That would make this number turn to -2/3 and this turn to 2/3. I don't want to deal with those fractions if I don't have to, so that's why I'm switching that. And then I'm going to multiply row 1 by -1 and put it in row 1. I guess I don't really need this put it in row 1. You have to switch both of them, so you're switching both of them. Because I'm not changing row 2, I am going to leave it. -1 times row 1 is 1, -2, 6. I always want to get the 1 in the top left corner first. Then I proceed down that column, meaning I want to turn this 3 into the desired number, which is actually 0. The way I do that is I multiply the row with the 1 in it by the opposite of that and add them. If I do -3 times this 1 plus the 3, it will give me 0. I get -3 plus 0. I want to put that in row 2, meaning I'm not actually changing what's in row 1. I don't actually want to change what's in row 1, even though here one of my steps is to multiply it by -3, because if I change what's in row 1, then I've lost my 1. I don't want to do that. Let's write some steps here, and hopefully this will clear up what we're talking about. In this spot, I'm going to follow this pattern. -3 times my row 1 entry is 1, plus my row 2 entry, 0. That's what I wanted. Here, I'm going to do -3 times my row 1 entry. I'm always looking at the matrix above. -2 plus my row 2 entry is -2. That is 6 minus 2, or 4. Then for this spot, I'm going to do -3 times my row 1 entry is 6 plus 2. -18 plus 2 is -16. Now I have the 0 that I want below the 1. I have my first column exactly the way I want it. We can only do operations on the rows, but we work through the columns. So we work to get the first column the way we want it. Then we move over to the second column and we work to get it the way we want it. Where this -2 is, we want a 0. Where the 4 is, we want a 1. Always get the 1 first, meaning I am not going to change my top row right now. The way I get my 1 is I multiply, that equation, or that row, row 2, by the reciprocal of what's in that spot. 1/4 of row 2, because that's the reciprocal of 4. And I want to put it in row 2. The benefit of this is it doesn't change the 0 that I had before that I want to keep. 1/4 of 0 is 0. 1/4 of 4 is 1. 1/4 of -16 is -4. Let me come up here. I'm going to recopy that. What did I have? 1, -2, 6. Just so I don't have to keep scrolling. 0, 1, -4. I am really close. My next goal is to turn this guy into 0. And then I'm done. I can read my solution right off. Oopsie. The way I get a 0, first of all, I want to leave that bottom equation. Notice that bottom equation is saying 0x plus 1y is equal to -4, which simplifies down to y equals -4. The way I get rid of this -2 and turn it into a 0 is I multiply the opposite by the row that has the 1 in it. So I'm going to do 2 times row 2 plus row 1 and put it in row 1. What happens when you do that, in this column at least, we'll work on the first column as well, but you get 2 times row 2 would be 2 plus -2. 2 plus -2 is 0. You're going to get a 0 in that spot. what about this spot here? 2 times row 2 is 0, plus row 1 is 1. The value in doing the operations in this order, in this way, is that we do not change all of the things that we previously had worked to get exactly the way we want them. We do have to find this spot. This one is going to be 2 times the row 2 number in that column, which is -4, plus the 6. That's -8 plus 6. So we get -2. We have the left side of this equals bar exactly the way we want it. 1's down the diagonal, 0's everywhere else. That allows me, remember, this represents x and y. X and y, and that's the equal sign and the constants over here. That allows me to say 1x, or just x, plus 0y equals -2. 0x plus 1y equals -4. Your ordered pair solution to this system of equations is -2, -4. Who feels like you need more practice? Yeah, for sure, right? These are not straightforward. Once you see the pattern, once it clicks, you'll start to see, okay, what rules do I need to use? I promise it'll click as you practice it. If it doesn't, let me know, and I am happy to work with you to get to the point where you know exactly what row operation you're going to do. We need to do some more practice, but this video is long enough. So we're going to stop, come back with another video and do more practice.